This is Chow ring. Classifying space. Vary the type a little bit. So let me recall. So basically, what I was talking about is it's quotient varieties by finite groups. I would like to understand their Chow groups. In a way, it's kind of trivial with rational coefficients, but somehow understanding Chow groups integrally in this case is hard. It's sort of a model problem for trying to understand things like torsion in Chow groups. But okay, so the sort of background is classifying space in topology. Topology, the classifying space of a topological group, this is called BG, of a, and please tell me if I'm writing too small. I'm sort of bound to be writing too small for the people in the back. You have a topological group G, the classifying space of it is any quotient space. So you write BG, this is BG, where BG is any contractible space with a free action. So EG has the homotopy type of a point, but it can't precisely be a point because I want G to act freely on it. Okay. And if you're careful about what a free action means, and you consider reasonable topological spaces are compact or whatever, then the important thing about this space is that it doesn't matter which contractible space you choose. The homotopy type of this classifying space is always the same. Okay, so skipping the hypotheses, basically it is true that the homotopy type of BG depends only on G. Right. Okay. So, for example, if G is just a discrete group, then this is what's called a KG1 space. It's the classifying space is a space whose, in that case, whose fundamental group is G and whose universal cover is contractible. But it makes sense for any topological group. Okay. And so, since this is well, the homotopy type is well defined, you can use this to define interesting invariants of a group. In particular, the cohomology. So we get a graded commutative ring, in particular attached to any group, any topological group. So just take the cohomology of this classifying space. Let's say with integer coefficients, or whatever coefficients you like. And so how, it's an intriguing mystery, say G is just a finite group, how does that finite group determine this ring, or how do you resolve properties of the ring from the group? It's not completely trivial. Yeah, and also, I should say, if G is a discrete group, then this is also called just the cohomology of G, because, the cohomology of G is a topological space, wouldn't be very okay, so just some quick examples would be that the classifying space of the group of order 2 you could view as RP infinity, real projective space, because the classifying space of the circle group you could view as CP infinity, and another familiar one would be the classifying space of the unitary group UN is the Grassmann can be viewed as. These are all sort of maybe you should thought of as up to homotopy equivalence, because the classifying space is really only defined up to homotopy equivalence. This is homotopy equivalent, or one way to view it is that it's the Grassmannian n-planes in C in the C to the infinity. And using these geometric descriptions, you can easily compute the cohomology of these spaces in these examples. For more complicated groups, it might be harder. Okay. So to get to algebraic geometry, what happens is that if G is an affine group scheme. So to be careful about the assumptions, say this is a finite type over a field. Okay, then what happens is that one can, how can I say it? One can define DG, one can define some kind of classifying space DG as a direct limit of smooth varieties over the field K. The reason I don't want to quite say, the reason I put quotation marks there is that I want to work only in the world of finite dimensional algebraic varieties, because as these examples show, classifying spaces essentially are always going to be infinite dimensional, or almost always going to be infinite dimensional. So yeah, I won't actually talk about infinite dimensional algebraic varieties, although clearly that's the sort of thing DG is. I'll just talk about sort of finite dimensional approximations to it. Yeah. So what are these smooth varieties that I use to make some kind of approximation to DG? So it's something very straightforward. You just look at representations of the group. It's a group scheme over K, so representation, I mean, a finite dimensional K vector space with G acting on it. And somehow the basic, at the core of this construction is that representations of G, or maybe at first you think of them as objects of linear algebra, but you can also think of them as algebraic varieties. So of course you could view that as affine space of some dimension over K, and then you can talk about the Zariski topology on it, and so on. Okay, so with that point of view, you can talk about, so let S and D be a closed subset that is Zariski closed, such that the group acts freely on what's left. And then, briefly, the idea is to think of, the quotient of V minus S by G as being some kind of approximation to the classifying space of VG. So at least I can say that V minus S is quotient by G. In this generality, it's a smooth algebraic space over K. You can easily restrict if you want to, just assume that it's a scheme over K. It makes no difference to anything. In other words, you just look. If G is actually a finite group, then it would always be a quasi-projective variety, and there's nothing to worry about. Okay. Right. Okay. So you get these smooth. In particular, even if G was some non-smooth group scheme, these quotient varieties are always smooth if you think about it. Okay. The reason that's convenient is that for smooth varieties, you have the Chow ring of algebraic cycles. And I can use that to make the following definition. Define the Chow ring of the classifying space of a group scheme is define Chow upper I of that to be Chow upper I of one of these quotient varieties for any pair as above, any representation B, closed subset S like that, such that the codimension of S inside B is greater than this number I. Okay. So maybe it takes a second to absorb that. So what I'm saying is if you want to define a particular one of these groups, Chow upper I VG, you just you find any representation you want, but it had better have pretty high dimension in such a way that the group acts freely outside some rather high codimension subset. And then just look at the quotient variety, take the codimension I, Chow group of that. So your group generated by codimension I cycles Lie rational equivalence. Okay, and then the basic thing is just the fact that is well defined. So just maybe proved by Burrell, Vygotsky, and me. was around 15 years ago, that so this group doesn't depend on which representation you look at, provided only that you have that assumption that the group acts freely outside large high codimension subset. Yeah, so we get a ring, we get a commutative ring called the Chow ring, the class-length space of an affine groups. Okay. And this is pretty easy to prove. I wasn't planning to prove it exactly, but basically it's just that you compare sort of two representations and the corresponding quotient varieties to the quotient variety of the direct sum of the two representations. That quotient variety is approximately a vector bundle over the one quotient variety. It's also approximately a vector bundle over the other quotient variety. And Chow groups sort of don't change when you pass one variety to the corresponding vector bundle. So that's pretty much the proof. You can make S bigger, sure, as long as it still has a definition. That doesn't change the Chow groups, right? Because like the codimension I Chow group, if you throw out some subvariety of codimension bigger than I, you're not changing. You don't change either the generators or the relations for that Chow group. The generators are codimension I subvarieties. The relations involve codimension I minus one subvarieties. So throwing out really really tiny stuff doesn't change the groups. Okay. All right. So let's see a few examples we can understand this. So take the multiplicative group. Which is, in other words, the affine line minus the origin viewed as a group under multiplication. Right. The convenient thing about this definition is if you want to compute those groups, you can take any representation you want as long as it's sort of big enough. So just let's take V to be affine n space with the multiplicative group acting by scalars. So we're just for any number n that we like. So in other words, it's the direct sum of n copies of the standard one-dimensional representation of this group. Then the multiplicative group, of course, acts freely outside the origin. And so, what does this definition say? It says that, Chow upper I, the cross-length space of the multiplicative group, is the Chow groups of the corresponding quotient variety, which is projective space, Pn minus 1, over whatever field we are. Like I said, this is defined over any field K that you like. The codimension Chow group of this class-length space is just the codimension Chow group of projective space, provided that that I is less than n. Yes. Right. That was this assumption here. And of course, this group is in this range. It's just as order to z. I'm just taking I to be a natural number, and in fact, this ring is not surprisingly just a cohomology ring, one variable. Where the generator is in degree 1, that is, U is in Chow upper Y. Okay, right, I hope that makes sense. So if you get any given Chow group of this class-length space, you just look at the corresponding Chow groups of some, finite dimensional projective space, and this is one of the calculations of Chow groups that we actually can do. And the sort of ring structure here is just saying that, well, it's the same as the ring structure here in this range of the groups. So of course, you could rephrase this by just saying that, what we're saying is that, so the class-length space of BG, of the multiplicative group, is P infinity, if you live in a world where you have infinite dimensional varieties like that. But I just avoid talking that way. Okay. Perfect. So what's another example? You can actually see something. So let's say what is Chow upper 1 of the group of order 2. And easy ways to do this, but let's just do this by hand a bit. So take let Z mod 2 act on two-dimensional representation by plus or minus 1, non-trivial element of Z-2 minus 1, then again, this group actually is free outside the origin. A2 minus 0, so what's going on? So the codimension 1 Chow group of the classifying space of Z-2, oh, let's say your say K is a field of characters not 2, let's say, it will be different characters 2. Then over any such field, Chow upper 1 of this classifying space is just defined because we're removing something of codimension 2. You can read it off on this finite dimensional variety. A2 minus the origin divided by Z-2. And this is something that in some form we all know. Right, so this codimension 1, Chow group of codimension 1 cycles, because this is a three-dimensional variety, it's the same as the Chow group of one-dimensional cycles on this quotient variety. And, also because this origin has codimension 2 in there, I don't change anything by throwing that origin back in, so I can just view that as Chow sub 1 of the affine plane line. Okay, this quotient variety is one that we all recognize. This is the affine quadratic cone in an affine free space. So xy equals z squared, and affine free space. This is affine plane line plus or minus 1. And what is this codimensional Chow group? What is this Chow group of one-dimensional cycles? It's also called the divisor class group of this cone. Well, it's isomorphic to Z-2. Right, as we all know from Hartshorne chapter 2. So this group is generated by any line through the origin. That's the generator of the Z-2. And why is that? Why is 2 times that element 0? Well, it's because you can draw a tangent plane to the cone along that line. Okay, so what does that picture mean? Well, the equivalence relation in the Chow groups is you're saying that this 0 set minus the poles of a rational function counts as 0. Now that plane is a 0 set of a linear function on that affine free space, which I can restrict to this cone. And that linear function vanishes to order 2 on this line, and doesn't vanish on any other, it doesn't vanish anywhere else. So sort of drawing that plane shows that 2 times this line is rational equivalent to 0. I guess another picture you could draw maybe over here would be that also on that cone, you could draw other planes and they would give you other relations in the Chow group, but they don't really change the picture. For example, if I intersect that plane with a sort of transverse, intersect that cone with a sort of transverse plane, I would find that like L plus M is equal to 0 in this Chow group. But that's not saying anything new because both L and M are equal in the Chow group. They're both rational equivalents to L. So this also just says 2 times the length of the origin. In other words, you can't find a plane, for example, that would cut the cones transversely in this one line. Okay. Yeah, that has some concreteness to the story. For any finite group, basically, yeah. So having defined this thing, you would like to compute it, and unfortunately, that's hard. I guess what happens is that, for some groups, you find that you can just sort of understand the quotient variety explicitly. You can see by hand that it's a rational variety, as happens in this case, and you can cut it, if you're lucky, into pieces that are open subsets of affine spaces. That also happens in this case. But it's not going to happen in general, and when these quotient varieties are not just unions of affine spaces at different dimensions, then it's not clear how to compute their Chow groups. Yeah, so I was just going to say that sort of rationally there's no problem. By the way, in general, I sort of started by defining this for any affine group scheme, but pretty quickly I'll specialize to the case where V is just a finite group viewed as an algebraic group over whatever field you like. View over any field. Okay. So yeah, just saying that the Chow groups tensor with the rationals are just a 0 for I greater than 0. and this is just sort of an easy argument. The same argument applies in group cohomology. It's just that you kind of consider the morphism from EG to VG. You can pull back elements of the Chow ring here to the Chow ring here, which is basically trivial. This is something like an interdimensional affine space. You can also push forward because this is a finite isomorphism of degree equal to the order of the group. I mean, you can pull back and push forward. You know, you can, and the Chow groups here are basically 0. That's enough to show that the Chow groups here are killed by the order of the group. And you get this statement. So somehow, so what I'm interested in is, can you compute these groups exactly, or maybe on P? Where the interesting case will be prime number speed is my view of this group. Okay. So one thing you can say is that one sort of general thing is that although group homology is nicer than I might say that in general we're always going to have a homomorphism from the Chow ring. Say the base field is the complex numbers. We're going to have a ring homomorphism from the Chow ring of VG to the ordinary cohomology of VG. Maybe say something about why that is, because if you just look at what these quotient varieties are over the complex numbers, then they are literally good approximations to the classified space of G in a topological sense. So because what we're doing is we're taking a space which is not quite contractible and dividing out by G, but it's nearly contractible in the sense that S has high codimension. V minus S has, for example, its cohomology is 0 in a whole lot of low degrees. So V minus S is kind of approximately contractible. And because of these things, the Chow groups of these varieties map to their ordinary cohomology, which is pretty much the same as the ordinary cohomology of VG. Okay, so you have a homomorphism like this. It's certainly not an isomorphism in general, for one thing, because Chow I is only going to map to the even dimensional part of the homology. But even there, it's not going to map onto all of that in general. And sort of one strange thing is that there are algorithms to compute group cohomology. There's certainly no algorithms to compute this. Oh yeah, about that, that's a question. So it is, are these groups finally generated really groups? I mean, we don't know that. It's another question for all groups, all finite groups, for example. It's frustrating. So they're torsion killed by the order of the group, but we don't know whether they're finally generated, which would imply that they're actually finite for finite groups. But that's sort of an indication of how little we know about these things. On the other hand, when you actually do manage to compute these things, one nice thing is you often find that they're sort of they're nicer than the ordinary cohomology. So let me try to say something about that. In examples, Chow ring VG is whenever you can compute it, it turns out to be somehow simpler ring than the ordinary cohomology. So, I mean, one thing that comes up in the calculations that helps to show why this is that, I guess sort of, this is partly because of, I might say, the basic exact sequence for Chow groups, which I'll write down here. So, for X scheme over some field and S, let's say closed subset or subscheme, you have an exact sequence that relates the Chow groups to the subset, the closed subset, the Chow groups to the whole variety, and the Chow groups to the open complement, and then comes a zero. So in topology, I guess specifically for L-more homology, you would have a similar exact sequence, but you wouldn't have a zero on the right here. This is what I'm saying is that the fact that there's a zero there is sort of a good feature of Chow groups that you don't have for cohomology. So why is that zero there? Well, it's because if you have any algebraic subvariety here, those are the sort of things that generate this Chow group. You can take its closure, and that is an algebraic subvariety of X. And somehow that's a very distinctive feature of algebraic geometry. Topology, if you have some kind of cycle there, and take its closure, it will just be a mess and not represent anything in homology. Right, that's somehow that helps explain why some calculations work out better. So, for example, this implies, for example, that any, if you have any non-empty open subset of affine space, then its Chow groups are just trivial. Chow over IU is Z in degree 0 and 0 in other degrees. Because that's true for affine space, and this tells you that the Chow groups of affine space map onto the Chow groups of any open subset. Whereas, of course, the cohomology of such an open subset could be more complicated. So an example of something general you can say about how Chow groups, this sort of Chow group is nicer than ordinary cohomology is the following. You can say that, so let's see, GB, again, I guess this is for any group scheme again, over a field. And if you look at these Chow groups and you localize them with respect to some prime number p, I guess any prime number p, then this is generated by Chern classes of representations if I is at most p. So maybe should at least try to explain what this statement means. Or any prime number p. So let me at least address what that statement is saying. So if you have if W is some representation of G, again a representation over the same field K, then you can use that to produce a vector bundle, an algebraic vector bundle on, well, I would like to say on VG, or if you prefer, on those finite dimensional varieties that are approximating the Cosine space. Yeah. Do I have anything special to say about that? Sort of just by descent, or whatever you like. You take the flat vector bundle in the topological sense, associated with some representation of a fundamental group. You get an algebraic vector bundle, and you can take Chern classes of that bundle, or in other words, Chern classes of the representation that live in the Chow groups of GG. So yeah, so what I'm saying there is that you work P locally for some time P, and in some decent range, the Chow groups consist entirely of they're sort of constructed entirely in terms of representation theory, which is kind of miraculous. Maybe the point to make is that this is not at all true for group homology. Yeah, the proof, how would I say it, sort of combining two things, one that is Thomason's results on equivariant K-theory. So, in a sense, Thomason showed that the K0 group of BG is just a completed representation layer of the group, which is like a theorem by Atiyah in topology. So, so my difficulties in computing the Chow ring are disappear completely if you looked at K-theory, K0 instead of Chow groups. There we somehow know exactly what it is. And then the Riemann-Roch theorem tells you how to relate K-theory to Chow groups. It's a very simple relation if you tensor with rationals. And if you want to work P locally, then it works very nicely, but only in this range of dimensions. That's sort of a quick summary of why that is. Right. So that's sort of like positive news about Chow rings. In that way, they are nicer than cohomology. And I guess what you can do is, if you're trying to compute Chow rings, you can try to reduce as much as possible to calculations in low degrees, where you can throw this theorem at. And that works fine, sort of for relatively small groups. So I just finished a book on this stuff called Group Cohomology and Algebraic Cycles. So I'll hereby advertise it. Let's see. A2, which is not. Let's see. Right. So the sort of thing I can show there is that for relatively small groups, Chow groups are sort of under control. So here's one statement. So use my fancy chalk here. I should thank the organizers. I understand this is the famous Japanese chalk. So let's see. Right. So one thing you can say is that if G is a P group, a group of order, a power of a prime number, maybe I should pause about that and say that in group cohomology in general, or also in this situation, the main problem is to understand, say, the Chow rings of P groups, because by this kind of transfer argument, if you want to understand the Chow groups of any group, sort of P locally, well, that will embed into the Chow groups of its P solo subgroup. So somehow the main issue, if you want to, for example, things like whether the groups are finitely generated or not, that completely reduces to the same question for P groups. So anyway, if you have a P group which is not too big, with, for example, order it must P to the fourth for P odd, or it must 32 with P equals 2, somehow then everything is as nice as could be. Then the Chow group of PG is generated by transfers of term classes of representations. So I need to maybe spell that out. So transfers are these, in algebraic geometry, it should just be called push forward. They're maps from Chow groups of the subgroup to Chow groups of the bigger group. If we were talking about algebraic groups, this would be for H inside G of finite index. So you have to look at sort of representations not only of G, but also subgroups of G, but at least you get a kind of algebraic description of this term for these pretty small groups. And yeah, somehow the trick is to kind of, so the definition involves, the Chow ring involves, higher and higher dimensional representations, but somehow the method for this theorem is to try to reduce the calculations as much as possible to just working with one representation, the smallest capable representation you can find. And for these groups, most of them have a capable representation of dimension P, so you kind of can reduce the calculations to, you can computing Chow I in for I equals P, and then you can throw that here. Right. Okay, and I want to say something about the base field in that theorem. The base field is pretty much anything. So that theorem works on any base field K. And you say that it's characteristic not P if you're talking about the a P group. Chow group's characteristic P would be totally different. So which contains enough roots of unity. E groups of unity, where E is the exponent of the group, which means the least common multiple of the orders of the elements. So you have to assume that you have some p roots of unity or p squared roots of unity or something. But with that assumption, then you get, in some sense, the same Chow ring for all the fields of that property. Maybe it ultimately comes down to this fact, because sort of the representation theory of the group is pretty much the same for all fields as long as they contain enough roots of unity. So you don't get any sort of more representations if you look at representations over a bigger field. Okay. So this is all kind of like good news, and then comes the bad news. All right. Let's see. Yeah. So I mean, I wondered if this might be true for all finite groups. Could it be that if you look at, is the Chow ring of VG sort of independent of the base field, as long as the field contains enough roots of unity? And in general, the answer is no, as I'm about to say. So, stay with here. So that's, let's see. So there are groups G of order p to the fifth for any odd prime p. And also there's some groups of order 2 to the 6th, so that this kind of statement fails in the sense that such that let's say the Chow ring of such a group, you consider it over Q bar, so a field that's big enough to contain all the roots of unity. Well, the Chow ring changes when you go to a bigger field. This map is not onto for some field that's bigger than Q bar. So, yeah. So there are some slightly more complicated finite groups where the Chow ring actually does sort of change when you increase the base group. Yeah, I might say that if F is algebraically closed, then this wouldn't happen. There's a theorem by Suslin's rigidity theorem that would say that if you go from Q bar to a bigger algebraically closed field, then these groups would stay the same. Since it's because of the torsion Chow symbol doesn't change when you go from one algebraically closed field to a bigger one. But for some other non-algebraically closed fields, it does change. And yeah, it means that and all the methods for this positive result, which so we're finding independent of the field, are going to have to change for these more complicated groups. So yeah, there's sort of two things to try to do: either say something about why that is, or make some more questions about what's going on. Let me mention some questions because that's somehow more important to get across. Some questions about this would be, so one, if you take one of these, so I'll describe sort of what these groups of order p to the fifth are. One of those where the Chow ring does depend on the base field. One might ask, actually, what is the Chow ring in terms of the field? It's going to depend on the field, but in what way does it depend on the field? Maybe it involves things like the multiplicative group of the field modulo p, something like that. But I really don't know that at all. Okay. Yeah, I think maybe the other questions will. I guess yeah. So another question that makes sense now would be: so is it true that at least these groups could they always be finally generated abelian groups, at least if K is not very close. It's a finitely generated abelian group. Let's say for all finite groups G, if K is not very close. Right. So I didn't say this, but as a sort of once you prove this kind of negative statement, it's easy you can produce other bad news. In fact, and in such an example, you can choose the field F so that the Chow groups of this of BG over that field are not finitely generated. For some okay. Right. So over some rather messy field, these Chow groups are not finitely generated. But what happens over an algebraically closed field? Don't know what to expect. So there's some questions. Yeah, and I'd like to say something about how to prove that these negative results. Yeah, I say they're negative results because I'm sort of saying that in some cases these Chow groups are vague or depend on the base field, but I really don't know how they depend on the base field. Okay, so yeah, so one issue is, yes, how do I figure out which groups I'm talking about to get these strange examples? And I had an idea of where to look because there are these results first by Saltman and later by Cohomology, who showed that so there are finite groups for which these quotient varieties of a vector space by the group acting linearly is never rational. Never meaning that it doesn't matter which representation V you look at. So more precisely, any two of these quotient varieties they're always stably birational to each other, and they gave examples of finite groups such that these quotients are not stably birational to projective space. And once you check out for one of these quotient varieties, it's equivalent for all the other quotient varieties. So how did they do that? The idea was to use unramified cohomology, which I'll quickly define. So let's say this for a variety x over field. Hey, let's say okay, unramified the unramified cohomology. So it is actually just a invariant of the function field as an extension of the little field K. Is finite, so I unramified cohomology of this function field with coefficients, let's say it's sigma p. It's the subgroup, the cohomology, Galois cohomology or Tal cohomology of the function field, which in turn you might think of as the direct limit of the cohomologies of smaller and smaller non-fields and subsets of X. It's the set of classes there such that U extends to an element in H by Tal of any sort of codimension 1 local ring of X. Let's see. Which extends to there for all irreducible divisors D. Okay, so yeah, so in particular, let's say if X is smooth projective, then an element in I cohomology of a smooth projective variety maps by restriction into an element here, and it certainly has this property. So you get a map from just the usual cohomology of any smooth convectification into this group. But I mean, the benefit of this group is that it's almost by definition birational. And Cohomology and Saltman were able to just compute this group explicitly for these classifying spaces, at least for H2. So they gave an explicit description in terms of group cohomology of this unramified H2 group for BG, and they found some small examples of B groups for which that this thing is non-zero, I should say. So if in particular H2 unramified of some variety, coefficients is non-zero, and this is not stably rational. I'll give a formula for how to compute this in the case where X is a quotient variety. Yeah, and once you get a formula for this, you can see that sometimes it's non-zero, and that's what happens for these. There are some groups of order p to the fifth or 2 to the 6th, such that unramified cohomology is non-zero. Unramified cohomology for quotient varieties, but I might also just call that the unramified cohomology of AG. Okay, and then the issue is, how do you go from knowing that unramified cohomology of some varieties is non-trivial to saying that, in some sense, these Chow groups are non-trivial, in the way that, in the sense that Chow groups increase when you extend the extended field. Sort of thought for a while that there could be some connection like this, but I didn't know how to do it until recently. So that's impossible to write. So let's see. So it goes in 2 steps. So 2 steps are so I'm going to consider the following sort of situation. So let X be a smooth projective variety over some field, and let U be a non-empty open subset in there. So the situation that I have in mind is where U is going to be one of these quotient varieties by a group. That's a smooth, non-compact variety, and I just let X be some for any smooth compactification of that. So we're in characteristic 0 where so second compactification exists. Okay. So in that situation, I want to say how unramified cohomology is related to the Chow group. So what happens is, sort of first, there's a connection between unramified cohomology and 0 cycles. So this is first. I think I attribute this idea to Victoria and Han and Sujata. Let's say if you have a variety that has some non-trivial unramified cohomology, let's say K is very, very closed. You have a variety, so it's definitely not rational for a kind of measurable reason. Then its Chow group of 0 cycles actually does depend on the field. Right. So the thing is, sort of knowing about unramified cohomology kind of directly tells you something about the Chow group of the smooth compactification, according to what I'm saying is that the Chow group of 0 cycles on that compactification is somehow non-trivial.
Is F, can the big F thing sort of,
yeah, sure. Okay, so basically what it is in that case is just the function field of your variety. In fact, why don't I sort of draw a picture relevant to this group.
Is it the generic?
Yeah. I mean, you're with me. So in this case, the field here to me with function field of X and stuff. So let me draw some relevant pictures. So this is supposed to be a picture of x cross x for a variety x over a field. Inside there we have this interesting subvariety, the diagonal. And inside this picture, you can consider the generic fiber of this first projection. I think this is the first copy of x. So inside there, you have the generic point of x, which is spec of the function field of x. And you have the generic fiber of this map, which is, well, x extended over the function field of x. So it's x is an n-dimensional variety, and this is n-dimensional. This is 2n-dimensional. And in particular, the generic fiber of delta is a zero cycle on this, I mean, it's the furthest point, I guess, on this variety here. So the class of the diagonal can be viewed as an element in Chow 0 of x over the function field of x. Notice that this is n-dimensional in this world, but it corresponds to something zero-dimensional. Can't really draw it very well in this world, just because that's what happens to dimensions of subvarieties. I mean, like a j-dimensional subvariety on this generic fiber corresponds to a j plus n-dimensional variety on this product. Okay, so the thing, yeah, so to understand why that sort of thing could be true, think about it contrapositively. Suppose that this map on Chow with zero cycles was always onto for all attention fields, in particular for this field, then that would imply that the class of the diagonal would be equal to the class of some zero cycle just coming from x over your original field. Okay. And that's sort of quite a strong assumption, because that would mean that, that's sort of a statement about algebraic cycles here, but it would imply something about algebraic cycles on the products. We'll draw another picture. What does it mean if two cycles are sort of equal on the generic fiber? That means that, on the original variety, they're equal modulo some kind of lower dimensional stuff. So that would give, actually equivalence on x cross x of the form, the diagonal would be equal to, say, excuse me, I try to stick with my notation. X product with some zero cycle on x plus b, where b is some algebraic cycle with an n-dimensional cycle on x cross x, but where I can say something about its support. Supported on, say, s cross x for some closed subset s, which is not the whole space. So you make this assumption on the generic fiber of this map, it implies that on the map, on the original version of the map itself, the diagonal becomes equivalent to something like how's my picture? Alpha cross x on the one hand, and plus some other cycle b, which is sort of supported over not all of x in the other direction. Right. So, and the argument for why that implies something about unramified cohomology is just that you can use cycles on x cross x as correspondences, and they give you a map from, say, the unramified cohomology of one factor to the unramified cohomology of the other factor. Now, the diagonal corresponds to the identity map on unramified cohomology, but if you apply one of these odd-looking cycles, you'll find that you get essentially 0 or something on unramified cohomology. So that's sort of this kind of decomposition of the diagonal would imply that unramified cohomology is basically trivial. And yeah, so sort of then the last bit is so I said all I want to say about why varieties with unramified cohomology have sort of non-trivial Chow group of zero cycles. This is for I'm thinking here of x as a smooth projective variety. Yeah, but unfortunately, what I'm really interested in are Chow groups of these non-compact varieties, and Chow groups of the compactification maps onto Chow groups of this, but a priori the Chow groups of this could still be small. Yeah, so there's another argument, but fortunately the same kind of trick about decomposing the diagonal. Sort of for the next and final part of the proof, you argue that if the Chow groups of your open subset U in this sort of picture, if they were kind of trivial in the sense that they didn't change under field extensions, U, you argue that this was not true for all I and all fields containing your little k, then something would happen. Well, then you would have a similar effect about Chow group of zero cycles on the compactification. Then Chow 0 of x mapping to Chow 0 of x would also be constant in the same sense. That would be onto for all fields F containing a little field. And yeah, so you put that together with this other fact, that applies to what I said. So that for these groups of order p to the fifth, where the unramified cohomology is non-zero, the Chow groups of this sort of quotient variety have to be increasing with the base field. So I don't really have time to say something about why this is, but I mean, I would say basically it's the same kind of argument about decomposing the diagonal, so that you just sort of analyze what this would tell you, starting with, at first you have to look at f equals the function field of x, but you end up having to look at other fields too. But yeah, sort of, you analyze what that kind of surjectivity statement would tell you about decomposing the diagonal. Yeah, and somehow the beautiful thing about this kind of argument, which is a classic kind of thing to do in algebraic cycle theory, is that you can look at this in sort of two different points of view. Like when you have a decomposition like that, it tells you one thing if you think about it as a correspondence from this copy of x to that copy of x, but it tells you some different information if you go the other way. And somehow that's the trick. That's how information about Chow groups of zero cycles of Chow groups of all different dimensions, but just on an open subset, end up telling you something about Chow groups of zero cycles, but on the whole variety. Because of this, because of the different ways you can think about decomposing the diagonal. Okay, so let's stop.
Any questions?
I mean, did you say anything about like the non-finite?
I mean, it's almost the same thing. So once you find that these groups can increase when you increase the field, you just have to wait. So you can increase it many times. I sort of take a direct look at the fields. That's not very. Beyond this, it's not exciting to agree.
So you say that this question of whether total change is related to a quadratic adjustment or compaction.
So my guess would be no, because so basically what people expect is that Hodge theory should be related to Chow groups sort of tensor with the rationals, and all this stuff is about torsion Chow groups, and it seems to be, as far as I can see, totally unrelated. Of course, maybe I think of something, but I feel like this is kind of a different world, really.
Questions?
No, you're right. I mean, I guess that's a hard question, and this is really just a statement about generators. Yeah, I mean, I suppose I think I don't have any general answer. I mean, basically, sometimes when you try to compute it, you can compute it, but there's definitely not any general answer like this. So, yeah, that's a good question.
Questions?